Levy, Mike Lowndes, Dave Somers, and Pinky Nelson, followed by Don Putty, who is the head of...
I know that I'll be able to look back on the tremendous amount of effort that went into getting us to where we will be on that day. Tremendous amount of human resources, monetary resources. But we will be in a position where the launch of Discovery on STS 26 will represent, I think, a tremendous maturity, maturing of NASA in learning from a terrible accident, and that we will be even stronger, and it'll be represented by the success that I know we'll have on that mission.
T-minus 15, 14, 13, 12, 11, 10. We'll go for main engine start. 7, 6, start. 3, 2, 1, 0, and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Roger, roll, Discovery. Crew confirms roll program. Houston now controlling. 3 inches, 104%. Discovery, go and throttle up. Roger.
7.5 years have passed since the launch of the first Space Shuttle. Over the 5-year period from 1981 to 1986, NASA successfully launched 24 shuttles. But during these missions, many lost sight of the unprecedented technical challenges involved in lifting a vehicle weighing more than 4 million pounds into orbit. Understandably, the emphasis was placed on the achievements of the shuttle program, as it quickly earned a reputation as a reliable and effective path to space. Early shuttle missions had demonstrated the versatility of the system. A total of 29 satellites were launched from the shuttle's payload bay. And when problems developed in some of these satellites, shuttle astronauts were able to retrieve them and bring them back to Earth for repair and eventual relaunch. The shuttle also served as a base for scientific experiments in a zero-gravity environment. The 2 Spacelab missions flown on the shuttle produced a wealth of high-quality data. Television audiences grew accustomed to seeing astronauts enjoying the effects of weightlessness. It seemed as if the Space Shuttle really was becoming the space truck, with a safe and reliable trip guaranteed every time. In July of 1982, after the landing of the 4th shuttle flight, President Reagan hailed the program's early promise.
The test flights are over. The groundwork has been laid. And now we will move forward to capitalize on the tremendous potential offered by the ultimate frontier of space. Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security.
For many within NASA, the President's confidence seemed premature. STS 26 Commander Rick Houck was involved in the program from the beginning.
I think that we, NASA, probably placed too much emphasis on how routine shuttle operations were becoming. I think to declare that the shuttle was operational, and whatever that meant after 4 flights, was simplistic.
We pulled the ejection seats out of the machines and we said we are now an operational space vehicle. And I'm sure that everyone who was associated with flight tests or had any involvement with the development and deployment of a new aircraft or a new system must have smiled quite a bit, because nothing can be that operational after just 4 flights. And in fact, nothing can be really very operational after 25 flights.
The first 4 years of the shuttle program had been successful, but predictably for a test flight program, there were anomalies.
T-minus 10, 9, 8, 7,
The Space Shuttle main
6,
engines were a prime concern.
4, 3, 2. We have an RSLS abort. We have an abort.
On mission 51F, a malfunction in a coolant valve led to a main engine shutdown 3 seconds before liftoff. The launch was delayed for 17 days.
Ignition and liftoff. We have liftoff of Challenger in Space Lab 2. The shuttle has cleared the tower.
In the rescheduled launch, everything seemed at first to be proceeding normally.
Houston now controlling. They'll be throttling down to 65% throttles on their main engines.
But a main engine shutdown 5 minutes and 45 seconds into the flight caused more problems.
We have a center engine down. Abort ATO. Abort ATO.
The original flight plan had to be aborted, but with only 2 engines firing, 51F still climbed into low Earth orbit. The eventual success of the mission obscured these early difficulties. A more long-term problem was the performance of the orbiter's tires and brakes on landing, and the situation was particularly severe at Kennedy, where the rough runway surface put added strain on the tires. The orbiter survived a brake lockup and a blown tire on mission 51D, but it was clear that landing was by no means routine. It was also apparent that any more serious failure in the landing gear would have disastrous results, especially on the relatively narrow Kennedy runway.
After a 2.5 million mile service call, the crew of 50...
NASA had been aware of the orbiter landing problems from an early stage. Meanwhile, a less visible problem was occurring in the solid rocket motors at launch. A number of the retrieved motors showed damage to the O-ring seals in the joints, with the potential for the leak of hot gases. Nevertheless, the rate of launches continued to rise.
There was very much a desire to try to make the shuttle pay for itself. And I think that's a no-win situation. The space program in the near term is not going to pay for itself. It's really an investment in the long haul. So I think there was too much emphasis on the flight rates. And I think with the magnitude of the workload and the criticality of the space shuttle systems, it's very unforgiving. That thing has just got to be perfect, particularly in the shuttle main engines and the solid rocket motor, or you're going to have a bad day.
That bad day finally came on January 28, 1986, with the launch of Challenger, mission 51L. This 25th space shuttle flight carried a crew of 7 under the command of Dick Scobie. At Mission Control in Houston, Capcom Dick Covey monitored Challenger's flight.
Roger, roll, Challenger. Good roll, flight. Raj, good roll. Three at 65.
65, Fido.
TDL confirms throttles.
Thank you.
Challenger, go with throttle up.
Roger, go with throttle up.
Fido trajectory.
GC, all operators, contingency procedures in effect. Don't reconfigure your console. Take hard copies of all your displays. Make sure you protect any data source you have.
Gene Thomas was launch director for 51L.
My first thought was, in my heart, I said, boy, in a minute I want to see the orbiter come circling back to Kennedy. And something makes you feel like guys like Dick Scobie can make that happen. But then all of a sudden my technical mind took over and said, hey, you can't get off the solids until, you just can't do that. There's no software, there's no hardware that'll allow you to do that. And then it hit me technically that couldn't happen and that the crew was probably
Gene Thomas was launch director for 51L.
My first thought was, in my heart, I said, boy, in a minute I want to see the orbiter come circling back to Kennedy. And something makes you feel like guys like Dick Scobie can make that happen. But then all of a sudden my technical mind took over and said, hey, you can't get off the solids until, you just can't do that. There's no software, there's no hardware that'll allow you to do that. And then it hit me technically that couldn't happen and that the crew was probably dead.
The death of the astronauts and the destruction of the Space Shuttle Challenger will forever be a reminder of the risks involved with...
Within days of the accident, the first steps were taken to implement a program for recovery.
As we move away from that terrible day, we must devote our energies to finding out how it happened and how it can be prevented from happening again. It's time now to assemble a group of distinguished Americans to take a hard look at the accident, to make a calm and deliberate assessment of the facts, and ways to avoid repetition. So I am today announcing the formation of a presidential commission on the Space Shuttle Challenger's accident.
Well, because we had such qualified people on the commission, engineers, astronauts, physicists, and so forth, they learned a great deal about the whole program. Of course, some of them knew quite a lot about it to begin with. But they got down and worked diligently on all aspects of the accident.
Rogers and the 11 other commission members began 4 months of investigation into the accident. Their work involved visiting the major NASA centers to inspect the testing and manufacturing processes involved in putting the space shuttle together. At first, the commission focused on the simple technical question, what caused the explosion? As the data began to accumulate, all evidence seemed to indicate that a failure of the sealing mechanisms in the solid rocket motor field joint was the most likely cause of the accident. It also became apparent that the record cold temperatures just before launch at Kennedy had contributed to the disaster. Sections of the launch pad were covered in ice as the overnight temperature fell into the 20s. The cold was also responsible for the first disastrous sign of trouble, which went unnoticed at the time of launch. 2 analysis cameras, stationed at different angles, revealed a jet of black smoke coming from the aft field joint on the right-hand solid rocket motor. The smoke was a sign of O-ring failure. Here's what should happen in the field joint at launch. The pressure in the joint at the time of ignition causes the bottom part of the joint, the clevis, to move away from the upper part, the tang. In normal conditions, the 2 rubber O-rings would fill the gap caused by this joint rotation and seal off the hot gas's path. But in the extreme cold, the O-rings lost their resiliency and the hot gas rushed past them. It was only prevented from escaping by the presence of a delicate glass-like seal formed by the superheated debris of the sealing mechanism in the first seconds after launch. For almost a minute, this seal was all that held back the hot gases inside the booster. 58 seconds into the flight, this seal gave way, probably shattered as Challenger was buffeted by severe wind shear at max Q, the point where maximum aerodynamic pressure occurs. The rest was inevitable. A tongue of flame leaking from the solid rocket booster led to the failure of the strut attaching the booster to the external tank. Once the booster broke loose and ruptured the external tank, Challenger was lost.
Well, I think most of us came to the conclusion that probably was the mechanical failure that caused the accident. But at about the same time, after about 10 days or so, we began to realize that there was a lot more to it than just a mechanical failure. We realized that there was a human failure involved, too.
In February, the commission returned to Washington to hear the testimony of those involved in the decision to launch Challenger. Quickly, the investigation began to focus on a crucial teleconference between NASA and Morton Thiokol, makers of the solid rocket motor. The teleconference took place on the night before the launch.
The teleconference started, I guess, close to 9 o'clock.
Thiokol's Alan McDonald joined NASA managers at Kennedy. Also on the line, NASA's Marshall Space Flight Center, and Morton Thiokol's plant in Utah. The question under discussion: could the shuttle be launched safely from Kennedy in freezing temperatures? Thiokol engineers at first said no, not below 53 degrees.
Well, that temperature brought a lot of strong comments and reaction from several of the NASA officials. I believe it was Mr. Malloy made some comments about when we'll ever fly if we have to live to that. One of the comments that came, and this was by voice recognition, I believe it was from Mr. Hardy at Marshall Space Flight Center, was that he was appalled at that recommendation. However, he also said that he certainly wouldn't fly without Thiokol's concurrence. He would not fly? He would not fly without Thiokol's concurrence.
But Morton Thiokol's managers clearly felt pressured by their NASA colleagues. In a private discussion, Thiokol managers and engineers reviewed their options.
I'm not sure exactly who asked for that, but
Thiokol senior scientist Roger Beaujolais found himself in the minority.
those of us who are opposed to the launch continue to speak out, and I'm specifically speaking of Mr. Thompson and myself, because in my recollection, he and I were the only ones that vigorously continued to oppose the launch. After Arnie and I had our last say, Mr. Mason said, "We have to make a management decision." He turned to Bob Blunt and asked him to take off his engineering hat and put on his management hat.
Back at Kennedy, Alan McDonald was stunned by his manager's change of heart.
Finally, the people from Thiokol in Utah did come back on the line and said that even though we had some concerns about the lower temperatures, that we would recommend that they proceed with the launch based on the fact that we felt the temperature data that we had was not totally conclusive. I told them I didn't feel very good about this recommendation, and in fact I made the direct statement that if anything happened to this launch, told them I sure wouldn't want to be the person that had to stand in front of a board of inquiry to explain why I launched this outside of the qualification of the solid rocket motor or any shuttle system.
There's no doubt about it that the senior people who made the final decision about launch were not notified about what had happened the day before. They did not know that there had been a tentative recommendation against the launch. Therefore, when they made the decision to go ahead, they thought there was no question that everybody below them had been satisfied that the launch should go ahead.
The Presidential Commission's final report was sharply critical of NASA, recommending a sweeping list of changes. 5 months after Challenger, the Kennedy launch pads stood silent. The nation's supremacy in space was jeopardized.
Morale after the accident, particularly in that summer in 1986 and maybe in the few months after the Rogers Commission report came out, was as low as I've ever seen it, and I was very concerned about it. You know, if you recall those times, we had, you know, all the bad news had come out, and we hadn't had the opportunity to reorganize the program and to make some personnel changes and to begin to make some progress. And I think people collectively were really concerned that we could ever dig out from the monumental task that it was.
Morton Thiokol's Wasatch Division, northwest of Salt Lake City, Utah. Here, work began immediately on a redesign of the solid rocket motor, identified by the Rogers Commission as the cause of the Challenger accident. Alan McDonald played a key role in the development of new hardware.
During the time frame from, I guess, the early part of the failure investigation until the official report from the Commission, we were looking at sketches and concepts to improve the joint in the areas that we already identified had some problems, or certainly could have been contributors to the overall problem.
The field joint on 51L and previous missions was a simple design that relied heavily on the ability of the two O-rings to prevent hot gases from escaping. If both seals were violated, then the motor became an explosive device. The redesigned SRM joint, incorporated in STS-26 and future missions, has a number of features which add redundancy to the two O-rings. The first is a rubber J-seal, which is designed to prevent hot gases from ever reaching the O-rings. At ignition, the engine's own pressurization forces the J-seal down and bonds it to the next motor section. Another new design element is the steel capture feature in the tang joint, designed to limit the joint rotation that occurred in earlier flights. A third O-ring provides additional protection for the primary O-ring. Three other elements, silicone filler, a longer steel pin, and custom shims provide further redundancy. And there's been another improvement. It's in the way that the field joints are checked for leaks. Before Challenger, the pressurized leak test sometimes pushed the O-rings out of their proper position. Now, the addition of a second leak check port ensures that both O-rings are seated correctly. New designs help to minimize the possible effects of poor weather conditions before or during launch. The outside of the joint is insulated with cork and rubber, and heaters keep the joint temperature at an even 75 degrees.
9, 8, 7.
It's a thorough redesign, and it requires thorough testing.
2, 1, fire.
Before Challenger, this static motor firing at Morton Thiokol was the only kind of testing of the solid rocket motors before flight. According to Marshall's J.R. Thompson, it wasn't enough.
In trying to make the shuttle pay for itself, it's my belief that we were cutting, I think, back too far in our ground test program. Once you start flying, there's no reason at all to stop testing on the ground. You've got to lead the flight activity with a very aggressive and ambitious ground test program, just so you can fly right down the middle of the road.
And testing is particularly important for the shuttle's solid rocket motors, as Morton Thiokol's Dick Davis explains.
The ones that are flown will have never been tested. And so to the extent that we can, we must ensure that they are as nearly identical to the parts that were qualified and demonstrated their ability to succeed, so that we can have confidence that the ones that are on the pad and are ready to be flown will be equally successful. The solid motors' reliability, the confidence that we have is entirely based upon their similarity to the articles that have previously passed qualification testing.
In the period since Challenger, the static motor firings have remained an important series of tests. They are the only firings of full-scale motors, identical to those which will fly on future shuttle missions.
2, 1, fire.
But now these test firings have been augmented by a series of other test environments which all share one goal: to discover exactly what happens in the solid rocket motor joints at the critical moment of ignition. Here at the Marshall Space Flight Center, Chuck Vibert is manager of the TPTA, the Transient Pressure Test Article. The test is designed to simulate as closely as possible the structural loads on the joint during ignition. It's the kind of test which wasn't carried out before Challenger.
Prior to 51L, I don't believe that Marshall understood the problem with the sealing mechanism, other than possibly a small number of engineers that work with it in great detail. We looked at the systems at the upper end of the motor, which is the recovery systems and the parachute systems that are used to recover the motor. They were tested in the typical NASA fashion, but for whatever reason, we were not aware of the problems with the joints. I think if we had been aware, then we would have been doing what you see us doing now.
Here's how the TPTA works. Unlike the flight solid rocket motor, which contains 11 motor case segments, the TPTA uses just 3, which form 2 field joints. Pressure is produced by a standard solid rocket motor igniter, and about 400 pounds of propellant, a mere fraction of that used in an actual shuttle launch. But the key elements in the test are a 1,000,000-pound weight resting above the test article and 3 struts attached to the side. At ignition, they exactly recreate the dynamic loads and stresses which would be created by a shuttle liftoff.
This type of simulation was conceived so that we could acquire a vast amount of information about the sealing mechanism. As such, we have many penetrations into the joint where we take up to 1,500 channels of data or information about the joint motion, pressure, temperature, and other effects, which would not be possible in a real motor.
The first transient pressure test took place at Marshall in November 1987. Just a few seconds in duration, but an important success for the booster redesign program. For later tests, NASA and Thiokol engineers introduced severe flaws into the joints in an attempt to get hot gases to the primary O-rings. The J-seal was flawed, and a portion of the third O-ring cut away. Now, the hot gases had a clear path from the motor interior to the primary O-ring. The second TPTA test, designated TPTA 1.2, had two important differences. Not only were the joints intentionally flawed, but pressure was contained inside the test article after ignition. For 120 seconds, pressures up to 950 psi built up inside the test article before finally being released. At the time of testing, TPTA 1.2 was the most searching examination of the redesigned solid rocket motor.
The bottom line of the results from this simulator and earlier simulation is that the redesigned sealing mechanism works as predicted. Okay, we're getting the deflections that we anticipated, and we have had no evidence of any blow-by or leakage.
At Morton Thiokol's Wasatch Division, the Joint Environment Simulator performs a similar function to TPTA, providing additional information about field joint seal performance in an environment similar to that of an actual launch. But the field joints weren't the only problem area. NASA and Morton Thiokol engineers also had to redesign the nozzle-to-case joint on the solid rocket motor. In 12 out of the first 24 shuttle missions, the O-rings in this joint were partially burned away during launch. The redesign aims to prevent that erosion by minimizing joint deflection at the time of ignition. Integral parts of the redesign are the inclusion of an interference-fit flap with the same sort of function as the J-seal in the field joint, a wiper O-ring to prevent adhesive from reaching the primary O-ring, a pathway which will allow any air trapped inside the seal to escape once the bond has been made, and 100 extra radial bolts to limit joint deflection. The redesign has been tested thoroughly in the Nozzle Joint Environment Simulator. And again, just as with the redesigned field joints, the new nozzle-to-case joints are working well.
The tests that are being conducted now, where we're deliberately building in flaws that are gross compared to the kinds of things that might get through a quality assurance check and balance system, have demonstrated that the design is tolerant of those kinds of flaws.
October 30th, 1986. Still 2 years away from launch, the shuttle Discovery, only partly refitted, was transferred to the Orbiter Processing Facility. The Orbiter is one of the most complex machines ever created, with thousands of components that must work perfectly on every flight. The failure of a single item could lead to disaster.
The failure of the O-rings was something that could have been prevented, and when we have a failure such as that could have been prevented, I think the implication is there might be something else lurking out there that could be prevented, and the program appropriately decided, as I say, to do a full review, top to bottom, of all the systems.
Critical items list review has been one of the most massive jobs we've done since the Challenger accident. It's involved many thousands of engineers. It's involved each of our shuttle projects, each of our shuttle major contractors, and every component and part in the shuttle system has been re-reviewed for its failure effects, failure potential, and those failure potentials have been categorized and listed by criticality.
The goal is to establish which parts fall into categories Criticality 1 and Criticality 1R. If a Crit 1 element failed, then both the crew and the shuttle would be lost. If a Crit 1R item failed, backup systems could keep the shuttle flying.
We've increased from 617 criticality 1 items that we understood and worried about before Challenger accident. We now have 1,450 crit 1s. One area that caused a great amount of that change was the main engines.
The Space Shuttle main engines have always been characterized as complex and critical systems. They work in an extremely hostile environment, where at ignition temperatures in the oxidizer pumps leap from 420 degrees below zero to 6,000 degrees above. But the main engines performed well over the first 25 shuttle missions, so there's no need for comprehensive redesign. Attention has focused on the turbine blades in the high-pressure turbo pumps. They've been modified to reduce the risk of chipping or cracking.
The job that we ask that engine to do, which is to take those propellants and burn them at high pressures and temperatures, and the designs it takes to accomplish that are without question on the forefront. It's always been characterized as at the forefront of technology. It requires patient attention to detail.
Testing of the main engines is carried out at the John C. Stennis Space Center in Bay St. Louis, Mississippi. Precise quality assurance controls, like this ultrasonic check of engine welds, are routine before test firings. The firings themselves aim to replicate as closely as possible the conditions that the engine will experience during flight. So most firings last for 520 seconds, the actual duration from ignition to main engine cutoff on a shuttle mission. Almost all tests also involve a gimbal program, with actuators directing the engine's thrust by angles as great as 7 degrees. And while the test is in progress, NASA engineers record up to 800 channels of data on the performance of main engine components. Since the Challenger accident, nearly 200 main engine tests have been run at the Mississippi facility. May 4, 1988, Space Shuttle Discovery, newly refitted, was brought out of the orbiter processing facility. 21 major changes had been incorporated into its design. Among the most serious criticality 1 items on the orbiter, the tire and brake systems, both identified by the Presidential Commission as lacking adequate safety margins. At NASA's Langley Research Center, they're assessing the kind of damage that is caused to the orbiter landing gear by each touchdown on the Kennedy runway.
Beginning launch sequence.
Water jets power a sled fitted with shuttle landing gear down a stretchered runway at speeds of over 200 knots. The runway surface is an exact copy of the Kennedy landing facility, ribbed and rough. The Langley research team checks the extent of the damage shown by the skid marks.
You can see the 2 outside treads have been worn down to nothing at this point.
And in the wear on the tires.
Because this is the one that you just saw.
This research has played a part in the development of modified tire and brake systems, which will handle the required loads more reliably. But landing at Kennedy still presents problems. The Director of Safety, Reliability, and Quality Assurance at Kennedy is Gene Thomas.
Indefinitely, right now, we don't have any plans to land at Kennedy. Under the ground rules that we're operating, where all landings, all in the mission landings will be at Edwards, I hope we don't use Kennedy. But, of course, Kennedy will be ready. We'll have a convoy there in case of a return to launch site abort.
Attempts are being made to smooth out parts of the Kennedy runway, where the original ribbed surface was designed to provide greater traction in wet weather. The runway should now at least be safe for emergency landings. For now, NASA's only option has been to buy another modified Boeing 747 to increase their capability to ferry orbiters from Edwards back to Kennedy. Another Crit 1 item has undergone design changes. The 17-inch disconnect valves in the belly of the orbiter, which deliver fuel from the external tank to the Space Shuttle main engines.
The 17-inch disconnect is a flapper valve that closes in each of 2 17-inch diameter lines between the orbiter and the external tank. One line flows liquid hydrogen, one line flows liquid oxygen. And so they're very large and very critical parts.
It's a sensitive part of the design that was originally suspected by some as the cause of the Challenger accident.
So during the period following the Challenger accident, we elected to introduce a design which put a mechanical latch in to hold the valves open while they're being used during the boost phase. And that change has been made and implemented and tested and is now installed in Discovery and will fly in STS 26.
Another addition has been the reintroduction of an escape system. NASA's first proposed design would have used tractor rockets to pull the astronauts out of the orbiter. Ultimately, this design was judged to be just a little too risky. There had to be a better way.
I had always felt like there was a place on board the machine for some kind of an egress system, some kind of an escape capability over what we had, which was virtually nothing. I had always felt like we could at least have backpacks, some sort of parachute on board, that if we got down to where we couldn't land on a runway out over the ocean or some sort of a scenario like that, that we ought to have some capability to run down to the side hatch and jump out.
And that's exactly the capability that the finally approved and accepted design will provide. These test jumps from a C-141 show the simple concept.
Green light.
Astronauts will slide away from the orbiter on a telescoping pole.
All clear.
And once they're clear of the aircraft, make a parachute landing.
It's going to be a little bit more of a feeling of confidence just knowing that if we absolutely have to, if we have an emergency deorbit for a loss of cabin pressure or something of that order, that we have some capability to escape once we get down into the atmosphere.
In another element of preparation for the flight of STS-26, pilot Dick Covey, mission specialist Dave Hilmers, and Commander Rick Houck spent 430 hours working through launches and landings in a shuttle flight simulator. As the rate of launches built up during 1984 and 1985, this kind of preparation became increasingly compressed. Now, simulation supervisors can challenge the crew with a wide range of different in-flight problems, all represented with complete fidelity, right down to the visual display of a Kennedy liftoff and roll program. This is as close as most of us will ever get to sitting in the pilot's seat for a shuttle launch. But for Rick Houck, it's a serious business.
We train to a level that we would never, ever expect to see. Of course, we can't train for failures that we can't cope with. There's no point in that. So we wouldn't train to a Challenger scenario. There's nothing to be gained by that. But when we go fly, we are ready to cope with a multitude of failures in a variety of systems.
Okay, Houston, we're working a helium problem on the center engine. We see that. Discovery, Houston, negative return. Negative return. Houston, we'd like you to shut down the center engine for precaution now. Okay, center engine going down now.
There may be a time when there are so many failures that you have that you can't cope with them. But if you don't ever get to that point, if you're always successful, then they're probably not pushing you hard enough.
July 4th, 1988. Discovery was finally rolled out to the launch pad at Kennedy. But one critical test still remained. Flight readiness firing, a final test of the three main engines that would later power Discovery into orbit.
We have a go for main engines.
Flight readiness firing, a final test of the three main engines that would later power Discovery into orbit.
We have a go for main engine start. 7, 6. We have main engine start. The motor's up and running.
The success of the test showed that the technical problems have been addressed.
We have a go for a shutdown, and it appears everything has gone well at this point.
But there have also been management issues to confront in the years since Challenger.
When we looked at the shuttle organization, it was clear to me that there were a small number, but very important number of things that just had to be done. And they were done, and the program still is organized this way today. For one thing, I found when I came to this job as Associate Administrator for Spaceflight at NASA headquarters, I found very quickly that I didn't have the time to personally put the effort into being the director of the shuttle program. And so, number one, I decided that I was going to create the position at NASA headquarters of a full-time program director, and turned out that Arnie Aldrich was the individual that was chosen, and he had a terrific background for that. There were a number of changes for a variety of reasons, both at Morton Tharcall, at Marshall, and at the other centers. A lot of people felt that they would change at that time. Other people, for other reasons, were caused to change. The key to the future, I think, is picking the right person for the right job, and instilling in them the obvious need and realization that the Kennedy Space Center, the Johnson Space Center, the Marshall Space Center, our contractors and our program people for the rest of the shuttle program have got to work together as a team and help each other with our problems. It's can't be allowed to degenerate to us versus you. You know, the schedule's so tight, you've got to send me your orbiter sooner. So, you know, and it's your fault. That won't work in this program.
In the first 5 years of the shuttle program, weaknesses in management structure were compounded by an overly ambitious rate of launches. After a cautious beginning, the flight rate doubled every 2 years, and NASA's ultimate goal was to launch 24 flights a year.
I think probably, in all truthfulness, we were working ourselves an awful lot. We had one launch director, me. We had one good launch team. We had very few, not much of a bench, I guess you'd say, in football. We didn't have a lot of reserves. We had a lot of young people coming along that weren't experienced. I think even the astronauts themselves thought we were flying a little bit too much.
The flight rate didn't just put pressure on Gene Thomas and his launch team at Kennedy. It also led to an enormous strain on NASA's resources of spare parts, in particular for the orbiter. The other 3 orbiters were routinely cannibalized for parts in order to support a single launch. It was a situation that was getting out of control until the Challenger accident intervened.
Some of the things that you do away with are flight spares, some of the quality control procedures and plans. That's something you can do without, and usually that goes pretty early when you get a budget crunch. But now it's being done, and we're getting that kind of stuff. We're bringing our spares back up. As I mentioned earlier, spares was one of the things that had us behind the 8 ball before 51L. And we now have something like 90% of the flight spares will be delivered and be ready to use before we fly again.
New inventory systems have been introduced at the Kennedy Space Center to provide quicker access to spare parts. This accurate and efficient organization is designed to support reliability and quality assurance in the orbiter processing facility. And it should still work after the flight rate has again increased to the level that Gene Thomas experienced back in 1985.
We were successful, and I think complacency is what really got us. We were successful, and I think although we didn't push safety aside, I think maybe safety got to the back of our mind, and it really wasn't number one.
The presence of former astronauts like Brian O'Connor, chairman of a NASA safety panel,
Got a lot of work to do.
and Bob Crippen, deputy director of shuttle operations, has helped bring a new approach to NASA's safety program.
We had a very good industrial safety program, and we weren't very strong, I'm afraid, in terms of aviation safety. And I feel that that's one of the big contributions that the astronauts that we've had involved in the safety program brought in a lot of aviation safety knowledge, and I think that's been a very strong contribution.
For instance, these flight-suited astronauts getting involved in safety and production issues in the orbiter processing facility. It's a sight that would have been unexpected when the flight rate was at its peak.
Admiral Truly has encouraged any of us on the crew, me specifically, to attend all of the Management Council meetings. We're staying very close to all the issues on 17-inch disconnect, solid rocket boosters, main engine turbo pumps, and so forth. So I guess I'd say I'm just staying very well informed, and when I have an opinion on how things are going, I've found that it's been an environment that has welcomed discussion of things.
I think we needed to put into place a safety program that was much more visible and had a day-to-day aspect of it that pervades not only our managers, but the people on the flight lines, the people on the floor of the processing facilities. It just makes good sense.
Now safety and quality assurance are stressed both at contractor facilities and at NASA centers. At contractor plants, every step of the process is checked, verified, rechecked, and certified. Manufacturing follows redesign and testing as the third stage in a process that must be letter perfect from beginning to end. To the worker on the shop floor, these requirements may seem unnecessary, but the constant hammering at quality assurance is essential to a successful shuttle program in the future.
The challenge that the program has is to create the systems that will protect us from ourselves, because you cannot reliably assume that every person in every decision point is always going to be equally alert. You know, they're not. We're going to have good days, and we're going to have days when we're not so good. So we need the checks and balances built into the systems, both in terms of technical decisions, quality assurance decisions, launch decisions, that will protect us from days when we're not as alert and not as keen as we ought to otherwise be.
At NASA centers like Marshall, the same kind of attention to detail goes into the preparation for each element of the testing program. Here, engineering workers check for any trace of dust or corrosion that may be lurking under the lip of the primary O-ring groove. But it's the kind of check that must be performed perfectly and repeatedly.
The hardest part is not now, because we haven't started flying and everybody is very focused in terms of looking for the detail. The harder job is going to be able to do it for a decade and 2 decades. But we've got to do it. That's got to be the management objective, and that is to keep the people focused over the long haul. Otherwise, we're gonna end up back on the beach.
The successful launch of Discovery helped finally to erase some of the memories of Challenger at NASA. The 4-day mission saw all systems working perfectly. The launch of a second tracking and data relay satellite, the mission's main job, went off without a hitch. But even more important were the words of Discovery's crew.
At this moment, our place in the heavens makes us feel closer to them than ever before. Those on the Challenger who had flown before and seen these sights, they would know the meaning of our thoughts. Those who had gone to view them for the first time, they would know why we set forth. They were our fellow sojourners. They were our friends. Today, up here where the blue sky turns to black, we can say at long last to Dick, Mike, Judy, to Ron and Al, and to Krista and Greg. Dear friends, we have resumed the journey that we promised to continue for you. Dear friends, your loss has meant that we could confidently begin anew. Dear friends, your spirit and your dream are still alive in our hearts.
Discovery Houston, recommend vector transfer to the BFS. Discovery Houston, on glide slope. Winds are calm.
The landing of Discovery marked the renewal of America's manned spaceflight program. Rear Admiral Richard Truly.
The only way to have a really safe flying program, doesn't matter whether it's airplanes or space shuttles, is stay on the ground.
Gear down.
That's not what anybody in this program wants to do. We want to make it as safe as we can, and then we want to go out to the pad and go fly. The proof of the pudding is going to be 10 or 15 years from now, when we're clicking off shuttles, not in a routine way, but in a regular, supported way, with trained people, with the right kind of disciplines, and the right kind of resources. I think that that's the kind of recovery we're putting in place.
Roger, we'll stop Discovery. Welcome back. A great ending to the new beginning. Thanks a lot.
Every time. In July of 1982, after the landing of the fourth shuttle flight, President Reagan hailed the program's early promise.
The test flights are over. The groundwork has been laid. And now we will move forward to capitalize on the tremendous potential offered by the ultimate frontier of space. Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security.
For many within NASA, the President's confidence seemed premature. STS 26 Commander Rick Houck was involved in the program from the beginning.
I think that we, NASA, probably placed too much emphasis on how routine shuttle operations were becoming. I think to declare that the shuttle was operational, and whatever that meant after 4 flights, was simplistic.
We pulled the ejection seats out of the machines and we said we are now an operational space vehicle. And I'm sure that everyone who was associated with flight tests or had any involvement with the development and deployment of a new aircraft or a new system must have smiled quite a bit, because nothing can be that operational after just 4 flights. And in fact, nothing can be really very operational after 25 flights.
The first 4 years of the shuttle program had been successful, but predictably for a test flight program, there were anomalies.
T-minus 10, 9, 8, 7,
The Space Shuttle main
6,
engines were a prime concern.
4, 3, 2. We have an RSLS abort. We have an abort.
On Mission 51F, a malfunction in a coolant valve led to a main engine shutdown 3 seconds before liftoff. The launch was delayed for 17 days.
Ignition and liftoff. We have liftoff of Challenger and Space Lab 2. The shuttle has cleared the tower.
In the rescheduled launch,
Clears the tower.
Roger roll, Discovery. Crew confirms roll program. Houston now controlling. 3 inches, 104%. 3 CPUs, 3 fuel cells. Discovery, go and throttle up. Roger.
7.5 years have passed since the launch of the first Space Shuttle. Over the 5-year period from 1981 to 1986, NASA successfully launched 24 shuttles. But during these missions, many lost sight of the unprecedented technical challenges involved in lifting a vehicle weighing more than 4 million.
Mike Lowndes, Dave Somers, and Pinky Nelson, followed by Don Putty, who is the head.
I know that I'll be able to look back on the tremendous amount of effort that went into getting us to where we will be on that day. Tremendous amount of human resources, monetary resources. But we will be in a position where the launch of Discovery on STS 26 will represent, I think, a tremendous maturity, maturing of NASA in learning from a terrible accident, and that we will be even stronger, and it'll be represented by the success that I know we'll have on that mission.
T-minus 15, 14, 13, 12, 11, 10. We'll go for main engine start. 7, 6. We have start. 3, 2, 1, 0. And liftoff. Liftoff. Americans return to space as Discovery.
Pounds into orbit. Understandably, the emphasis was placed on the achievements of the shuttle program, as it quickly earned a reputation as a reliable and effective path to space. Early shuttle missions had demonstrated the versatility of the system. A total of 29 satellites were launched from the shuttle's payload bay. And when problems developed in some of these satellites, shuttle astronauts were able to retrieve them and bring them back to Earth for repair and eventual relaunch. The shuttle also served as a base for scientific experiments in a zero-gravity environment. The 2 Space Lab missions flown on the shuttle produced a wealth of high-quality data. Television audiences grew accustomed to seeing astronauts enjoying the effects of weightlessness. It seemed as if the Space Shuttle really was becoming the space truck, with a safe and reliable trip guaranteed.